Alright, so this video will have a sample problem that deals with the Reynolds transport theorem, touches on the difference between looking at a fluid system from an Eulerian or a Lagrangian approach, a control volume versus control mass, uh, you know, look at the system where the control mass is called system in your book, and even some discussion here about a material derivative shows up. So it's 4.67 in your book, which has this picture. So this is a 2D system. It's really flow in 2D, and what it says, and the the words are on the previous page, the description of the system. But we have this blob at some initial time t, and then we'll put our control volume coincident there. So like the control mass or the system at time t lies directly on top of the control volume, which is going to be fixed in time. But then after some delta t time, our control mass has moved, or our system has moved to a new shape. And we break down all of these different parts of the space into three segments. This segment is this is a section of the space where the system was originally but is no longer. Section 3 is the opposite, where the system is now after a delta t but wasn't in the original, wasn't the space taken up by the system or the control mass at time t. And then 2 is where the control mass was in this space originally and continues to be there after a delta t. And so here are the 4.67. This is the description, and I'll just, there's a lot of different properties given here. But what we need to ask is, what is du dt? So the material derivative of this big U quantity, where that big U quantity is the energy of the control mass at time. So here's my description of the system. We need to evaluate this du dt, the total change in U for the control mass, using first a Lagrangian approach and then a Eulerian approach, and then here is where we see the material derivative show up. Okay, so this big U is the mass of the control mass, or of the system, times this little u, which is the total energy of the control mass, where the total energy, internal energy here, is just the specific heat times the temperature, so the specific heat at constant volume. So this is the energy per unit mass, right? Because all you have to do is multiply this by mass to get to the energy. Some fluid properties are given, specifically the specific heat. The temperatures have changed from the initial time to a later time, all right? So that's going to cause some, we have to be careful with that, and we'll change the system a bit, right? And so that's why the system has changed its energy. And a small delta t, and the mass is composed of two slugs. The total mass of the system, or the control mass itself, has a mass of two slugs. And we know that, again, this breakdown of the three different segments, 10% of the mass in the original control mass, right, in that has left, right? So, and I have this nice little table here. So at time t, 10% of the mass is in 1 and 90% is in 2. And there's nothing living out here, right? That's because at time t, we've fixed our control volume to be the control mass at that time t. But after a delta t, after a movement of the flow, a movement of the mass, the particles involved have moved to this blue line, and also the temperature has changed, changing the energy. So there's a time change in the energy, but has moved to this new shape, which is now composed of sections 2 and 3, where now 2 still has 90% of the mass, and 10% is now moved out here. All right. All right, so a Lagrangian approach to this is say, let's follow the control mass and calculate the change in the energy over this delta T. So this may be the most straightforward approach. It should seem commonsensical. If you'll extend that idea a little bit, this is what our fundamental laws of physics that govern fluid flow talk about things. This is what we make statements about, is that if you just are a particle and moving with the flow, you have some fundamental restrictions. Your mass can't change, or the total mass of your particle and the big system of particles can't change. Its momentum can only be affected by external forcing, and the total energy must remain the same, but we can get external energy transfers through heat processes and work being done to a system. But regardless, the main point at this stage in the game, again, this is a tool we'll be able to extend upon later, but is that a lot of the way we talk about fluids and really the laws that govern fluids involve a Lagrangian approach, and this should come, at least from a qualitative standpoint, come as a common sense approach. So this is just saying the change in energy over time is just take the energy of the whole control mass at t plus delta t minus the energy at time t and divide it by the total time. Here we just need to plug in that u is just m times CV times the temperature, and the only thing that changes in time, so the mass of the control mass stays the same, the specific heat remains the same, but the temperatures change. So we just have a difference in temperature times our mass and our specific heat. Plug all their numbers in, we get a change in energy of 1920 BTUs per second. Okay, the associated Eulerian approach, where here let's consider a fixed control volume, where we fix the CV, what the control mass was at time t, and apply our Reynolds transport theorem. Okay, so this is now going to be a lot more work, and we're going to get to the same exact answer, but the idea with doing this is that going forward, our analysis on systems, analyzing systems this way will be a lot more easy. Even though our statements about fluids, our fundamental laws are a Lagrangian approach, we want to be able to analyze things where we can break down a system into points. Oftentimes we measure things at specific points, and that requires an Eulerian approach. It's really hard in practice and in analysis to follow fluid particles through a system. Instead, we want to remain at a fixed point and look at what properties do there, or many, many fixed points, I guess. So we'll consider the control volume drawn in the diagram and apply Reynolds transport theorem, where this intrinsic property is just the energy per unit mass. And if we plug this directly into the Reynolds transport theorem, we get that the total change of the energy of the control mass per time is equal to the time rate of change of this quantity integrated over CV. So this is going to be the density times the energy per unit mass, right? So that's just how much the CV itself, the control volume itself, how much energy it has. You can see this is a density over a volume times this energy per unit mass. Therefore, this really represents the mass times the energy. I'm sorry, the mass times the energy per unit mass. So it really represents the total energy within the control volume. Over here, then, we have fluxes of energy through the control surface. And back to our diagram, control volume is in the dashed pink line. We definitely have fluxes of energy crossing that in our small delta t. All right, so let's break each of these terms down. The time change term is a time rate of change of really the energy, the accumulated energy throughout the whole control volume. Plug in what tilde is here. The energy per unit mass is just CVT. And approximate that by saying this is a very small delta t. So we can just take this quantity times its volume at t plus delta t minus the whole integrand at t over the delta t. And that's because it's a small delta t. If we do that, well, what changes with time? Well, the excuse me, the density times the volume is just the mass within the control volume. So we have the mass within the control volume is the thing that changes here Also, the other thing that changes is the temperature. Okay, so here, the mass within the control volume. So this is the mass within the control volume at T plus delta T. Remember, the control volume is only 1 and 2. 3 is outside of the control volume. So we're only going to get 90% of the mass, whereas originally all of the mass was in our control volume. So that makes up our CV. This is outside our control volume. All right, so we have 90% of the mass at T plus delta T times the temperature at T plus delta T minus all of the mass times the temperature at the original time T. And then, by writing this 0.9 and a factor of 1 out front here, we're able to pull the mass and the CV out. All right, and at that point, we'll move on. We'll plug in numbers later. Noting here that this little m is the total mass of the control mass. All right, so now looking at the flux term. This is all the fluxes through the control surface. So this is really the flux of energy through the control surfaces, which we can represent as all of our energy fluxing out of the control volume over that small delta T minus all of the energy fluxes, coming into our control volume, making this is the net energy flux leaving our control volume. Well, look again at our picture. We only get, of our original system, of our original control mass, energy can only leave. It can't go in, right? Because we co-located our control mass at time T and our CV. So the mass can only leave. It can't enter. So we only get energy leaving our CV from our control mass, within our control mass, and there's nothing coming in. So what this is going to be, what has left in that small delta T? Well, it's the mass within that third section times its energy per unit mass at times T plus delta T. All right? And that's really the energy that has left. This is energy per mass, and this is the mass of what has left and then we have it's the time rate of change of that, so over the delta T. Plugging all this in, noting that our mass in section 3 is just 10% of the total mass of the control mass. This is what we have. So now we have the two terms going back here to our Reynolds transport theorem. This is our Reynolds transport equation. We have the time rate of change and the flux terms solved out, pretty well. So all this is in terms of is kind of known quantities. M, we have an idea what that is. We're given what that is. We know the specific heat. We know the two temperatures, and we know the delta T. At this point, we can just plug everything in and solve. And so that looks like this: the total time rate of change, the total material derivative of energy for our control mass, equals this time derivative term plus the flux term, the energy flux through the control volume, through the control surface that bounds the control volume. And if we look here, these terms are exactly the same. I mean, this first term is exactly the same there, except we have a 0.9 and a 0.1. Therefore, this is going to become complete. It'll have a coefficient of 1 exactly. So here we'll have just a change in temperature times mCV delta T. And if we compare that to our Lagrangian approach, that's exactly what we have right here. And as so our Eulerian analysis is a bit more complicated here, but we get the same number. We actually get the same final form of the relationship for the total rate of change of our energy and for our control mass. But going forward, having an Eulerian approach will make our analysis more straightforward and will allow us to kind of think about our systems as having a instead of following particles around, we can think about things as their spatial have a spatial dependence as well as a time dependence, and analyze systems that way.